Okay, any questions? Okay, as I said yesterday, today we will discuss about the issues related to the joint between beam and column. Normally, when we develop analytical model, obviously it's a central line model, so it's just a point. And whatever moments and shear force we calculate, we rarely give a second thought about this. What we are looking at is a point, is not a point. There is a finite size, and there are implications because of that. And particularly when the analysis that we do is only indicative. It's a very approximate analysis, and elastic analysis on top of it. And the behavior that we expect during even design basis earthquake, and even during the more severe earthquake, the behavior is going to be inelastic. So the beams are the moments developed in the beams. We design the technique to design is that we design the system such that hinging moment capacities are exceeded in beams, while the column capacities are not breached. Columns are designed to have much larger moment capacities, but even then the issue of the critical section that I mentioned yesterday, it is on the beam column interface, the where you have the from where the face from which you measure the clear span of columns and clear span of beams. So that leaves a rectangular or square portion or whatever, depends on the shape of the column anyway, which is not really paid attention to significantly, and that is a cause of concern. I mean, most of the problems, I mean, this problem, this lack of attention to this humble but very critical part of the building system has been the cause of several disastrous collapses during past earthquakes, because nobody paid attention. Beam structural members, when we talk of structural members, we only talk of beams and columns and structural walls. Nobody talks of the beam column joint. Have you ever heard anybody talking about beam column joint? Have you ever paid any attention to beam column joint so far? Anyone? Okay, so let me erase this thing and start. Okay, let me just delete this page. So let me start with the basic idea behind beam column joint, and then I'll show why it is so critical and how to design that. Let us take for the simplicity the most common, an interior joint. So you have beams framing in from both sides into the column. So let us say this is depth of beam, and let us say this is the depth of column. So in case of seismic load, what kind of moments do we have? There will be uh, moments in the beams, and there will be associated shear. In the beams, and obviously this would be there would be complementary moments in the columns. Okay, so let me draw by so these are the stress resultants in columns. And these are the stress resultants in beam. Now, one thing that you need to understand is this is the point. I mean, when we say beams are going to yield, the plastic hinges are going to form in the beam. So maximum moment, of course, is at this point. So there is going to be, if you look at it, there is going to be compression here, compression in the reinforcement. So compression, and there is going to be tension on this side. On the other hand, there is tension at the top here and compression at the bottom here in the beam. So how do you arrive at? I mean, let's say, how do I draw the bending moment? I mean, uh, the moment here, particularly, there will be point of contraflexion at the mid span. So the bending moment diagram that I draw will be, if I draw on the tension side, then for the columns I can draw this, let's say center line. So it will be somewhat here. It's a linear bending moment. It goes up to point of contraflexure at the midspan and similarly from here up to here. So this is the bending moment diagram in the columns. Now, if you look at this joint, the joint has to, the moment changes from here to here over this short span. Right, so at this point, this is going to be point of contraflexure at the center point, and and the moment goes from tension at the bottom to tension at the top across this distance DC. Okay, let me revise this. Right. So what is the gradient of this moment? The gradient of, what is the gradient of bending moment? That's the shear force, isn't it? So this is the total shear that is happening in the this panel zone is subjected, this beam column joint is subjected to this shear force by virtue of reversal of signs of the bending moment on two beams that are framing in, right? And this is only on the one side. Obviously the other orthogonal side, the beams framing in from the normal to the plane, they will also have similar kind of action. Now if I look at the shear force that normally we compute here, you will get an idea what is the shear force that we have here. Let's say out of any of these sections, critical sections as we call them, or let's say at the center point, because this shear force is of course constant, and this is going to be let's say if the moment is same here, MC, then it is going to be twice MC by DC. That is the shear. Now shear in joint due to moment reversals. Just a minute. हाँ नमस्कार नमस्कार. जी जी. हाँ. इनका एड्रेस प्रवीण कुमार से आप ले लीजिए. ये एडवोकेट है सिविल लाइंस में शायद. हाँ. Okay, so this is the moment reversals in or beams framing into the joint. And if we compute the actual shear force, I mean, this is obviously there is a shear force here. I mean, this is MC. There is a shear force in the columns. So if we look at what is the shear force, I mean, this is shear force that is coming in, and then there are issues related to the horizontal shears because of this uh, reinforce or the yielding of the forces in the beam, the horizontal forces in the beam, and those are also transmitted across. So that force will be, if you can do that, so there is compression here and there is tension here. So this is C1, this is T1, and this is going to be T1, or rather this is T2, and this is going to be C2, right? So if we assume uh, for as a first order that C1 and T1 are equal and C2 and T2 are equal, that's the yield force. I mean, we assume that I mean, in the case of dynamic earthquake loading, both ends are going to be yielding. So this is this may yield at one, this may be under tension at one time, compression at another instant of time. Similarly, this may be tension at one time and compression at another instant of time, and so on. So both of them still at top and bottom, they are going to yield. So we can compute the moment as because of this, and the total shear force because of these forces, if I compute here, then it will be the shear force coming from the column, and then plus whatever C1 plus C2 or T1 plus T2, right? Depending on, this is algebraic summation. So this is the quantities may get added up or subtracted depending on the their sense of action. So this is the shear force, and it leads to total shear due to horizontal actions. Now typically we only consider this at most this kind of shear force for design calculation, but the shear force that you have here, if you draw the shear force diagram might look like something like this. And then suddenly you will have this massive shear force which will be constant throughout the, okay. So this is the shear in joint, and this is the shear in columns. So you can see that the shear force in the joint is going to be very, very large compared to the shear force that we often compute in the columns. And that is why it is extremely important, and that's why makes this joint extremely vulnerable. Very high shear force because of very steep moment gradients across this very short width of the column. and that leads to very high shear force, and that shear force, this shear force in the joint may be of the order of 5 to 6 times the shear force that we have in the columns. And how do we design for this? First of all, this entire thing, joint, is highly inaccessible, very, very difficult to access. In case of reinforced concrete structure, you can imagine the difficulty of accessing this region, reinforcement cage. There are longitudinal reinforcements going in across, there are across the beam and across the columns, and then there are cross ties in columns, there are cross ties in the beams, and so on. So this particular, I mean, sometimes it is so difficult that people, unless you are careful and very vigilant in the site, uh, most of the time you will find that people do not bother about providing these stirrups in the beam column, in the joint region, or this transverse reinforcement, the joint. So due to difficult access, it is very difficult to provide adequate transverse reinforcement. To resist the extreme shear forces. So the problem now is, although it might be difficult, but there is no escaping that. You need to realize that what you are looking at in this shear, in this beam column junction, that's a major source, I mean, that's a major weakness. And if this fails in shear, obviously shear failure is a catastrophic, it's a brittle failure, and the entire thing will collapse into mechanism. The structure, although you may have designed the beams and columns very diligently, but if you do not pay this fine attention to the detail of beam column junction, beam column joint, then the entire thing comes to a knot, and there is going to be very severe catastrophic failure of the entire building. So it is extremely crucial that adequate shear reinforcement capacities should be provided. And now how does it gain? How do we provide the shear capacities? First thing, that is the everything that you have here in this beam column junction, it only depends on joint strength depends only on the bond and shear, because there is no flexural deformation, there is no deformation here. All that you have is bond strength, because if you look at it, it's a very, very demanding situation. On the one hand, this is at one end, this particular thing is under compression. At this end, this particular thing is under tension. So this is under tension and this is under compression. And similarly here, it is under tension, it is under compression. So this entire thing is very, very demanding on the bond strength. And if the yielding, the beam yield extends into this joint, then obviously there is going to be a uh, failure of the bond. There is no way those inelastic deformations in the reinforcement can be accommodated in the joint without uh, deteriorating bond. And once the bond deteriorates, the integral action is of course goes for a toss, and we are looking at severe loss of strength. And in particular, uh, if as you see, the joint strength depends, there are only two mechanisms, that is bond and shear, and both of them are very poor as a energy dissipation mechanism. So there is no hysteresis, there is no nothing to be gained by encouraging any kind of inelastic deformation or any kind of elastic capacity is being breached in the case of in the joint region. So it is always the best practice is to avoid any kind of inelastic deformation extending into the joint, and prevent ensure that the concrete under compression remains intact, the concrete strength in compression remains intact, so that it allows you to develop sufficient shear strength. Because if you look at it, so this is going to be, there are going to be uh, tension here and compression here, so the diagonal truss action is what is going to be very critical. So in all these aspects, it is extremely crucial that the reinforcement, transverse reinforcement that is prescribed for columns and beams, that should continue through the joint to the I mean, you need to find a way how to do that. I mean, it may slow the workmanship little, make it for a difficult uh, exercise in placing the reinforcement cage, but it has to be done. There is no getting away from the from this exercise. The transverse reinforcement, there is no way you can avoid providing any shear reinforcement in the beam column joint. And now, as I said, the bond is very important. If and we should avoid the failure of bond in case of joint. And how do we do that? How do we achieve that? Uh, the easiest way to do that is this is what we discussed earlier in the case of design of beams, that instead of uh, looking at plastic hinge developing at the beam column face where you have the maximum moment, instead of developing the beam column the plastic hinges in the beam developing at this interface, we move it away from this, some distance away from the column face, right? So that's how we do that. So to protect bond inside the beam column joint, it is preferred to move plastic hinges away from the beam column face into the span. So, so typically we saw that typical way is we move one one effective depth away from the column face, and the way to do that is provide additional reinforcement and additional flexural reinforcement and additional shear reinforcement as more than what is required to as we achieve from the arrive from the uh, flexural capacity, reduced moment capacity at the section. So that reduced capacity is provided at 1D distance away from the beam column face, and within that 1D we provide for the larger moments and ensure that the beam uh, doesn't yield at the beam column face, and if it doesn't yield in the beam column face, then the inelastic deformations will not protrude, will not extend into the joint, and then the bond will remain intact, and therefore that will save the beam column junction from uh, unnecessary distress. So that's a very critical thing that you should account for. Don't just blindly believe on the results of your analysis, uh, computer model analysis that are only central line models, and central line models do not account for this beam column finite size of the beam column junction, and the fact that there is a finite width over which this moment reversal in the beams that are framing into that joint is happening, and that leads to a very high gradient, leading to very high shear force in the uh, beam column junction, and that shear force leads, obviously there will be diagonal tension, diagonal compression, and it has to be taken care of by individual capacities, the concrete compression and the shear reinforcement transfer steel that has to go there, and obviously it is going to be in the both beam as well as columns. So transverse reinforcement of columns as well as beams, they have to continue in the joint. You cannot just stop. It's simply not permissible to stop the transverse reinforcement and have the only longitudinal reinforcement going through the beam column joint. The transverse reinforcement has to go at the same spacing in the beam column joint as well. And then we move the plastic hinges away from the beam column face, and that will prevent the inelastic deformation, yield deformation extending into the joint region, and that will save the joint, and that will save, I mean, that will make the design, whatever you have worked out as a presumably strong column, weak beam, it will continue to behave in the same way as strong column and weak beam, and inelastic deformations will only happen in the beam at distance away, I mean some distance away from the beam column face, and that will be manageable, so to say, repairable damage, and all should be well. So I'll stop here for today. Next lecture, Tuesday, we'll start with structural walls and try to finish it off
Sir,
as soon as possible. But you should also remember that this beam column joint that we have discussed, I mean, the same behavior happens for steel structures also, and it is more vulnerable there because panel zone is only a very flimsy web, right? So you need to provide for web reinforcement or web stiffening in order to increase its uh, flexure, in order to increase its capacity so that it doesn't fail. Yes, please continue.
सर ये नोट्स सर मिल सकता है सर जिस पे आप लिख रहे हैं सर,
हाँ
कुछ क्लास छूटी है।
ठीक है, वो तो मैं अपलोड तो करता हूँ अपने इसमें क्या वो जैम बोर्ड में तो अपलोड करता रहता हूँ, तो आई विल प्रोवाइड एक्सेस टू दैट जैम बोर्ड.
ओके सर, थैंक यू सर।
सर
यस.
सर ये जो हमने शेयर जो है जॉइंट पे हमने जो शेयर का डायग्राम वो मोमेंट का डायग्राम बनाया था सर, फिर हमने शेयर निकाला 2mc/dc करके।
राइट.
तो सर यहाँ पे हम बोल रहे हैं कि ये जो है वो मोमेंट रिवर्सल एंड बीम की वजह से शेयर आ रहा है,
हाँ.
बट सर मोमेंट तो हम कॉलम का ले रहे थे यहाँ पे।
नहीं नहीं नहीं, मोमेंट का कॉलम का नहीं है. ये मोमेंट यहाँ का है, आई मीन ठीक है, कॉलम का भी है तो इसका भी आएगा. ठीक है, सो लेट्स से सो कॉलम का मोमेंट है, दैट्स राइट. सो वी आर ड्राइंग द कॉलम, वी आर अप्रोचिंग दिस जॉइंट फ्रॉम द कॉलम, but I could have approached this joint from the beam as well, isn't it? I could have drawn the bending moment diagram like this, है ना?
जी सर, जी सर।
So it will be the same thing. So the considerations are same. Of course, the joint is under moment both from columns and the beams, and but because the moment in columns are going to be higher than the moments in the beams, and therefore we use column moments for the computation of joint capacity. What is the maximum shear force that will be expected in joint, right? Although mechanics wise column moments have to be equal to the beam moments, sum of column moments has to be equal to beam moments.
जी सर। सर एक और चीज, सर जो हम जॉइंट को बोल रहे हैं कि ये वल्नरेबल होता है, क्या ये सिर्फ अर्थक्वेक वाले टाइम पे वल्नरेबल होता है, फिर नॉर्मल हम जब डिजाइन करते हैं तब भी
ये
उतना ही
तो अर्थक्वेक की
वल्नरेबल
वजह
होता
से
है?
ये ना, ये जो मोमेंट पैटर्न है दिस इज ओनली बिकॉज ऑफ द अर्थक्वेक. ग्रेविटी लोड में ये मोमेंट पैटर्न आता ही नहीं है.
जी सर, हाँ।
है ना? So gravity load में you don't have this issue at all. It's only under the lateral load that you have this issue that sign of moment is different on the two opposite faces of the column.
यस सर, हाँ।
ठीक है? So I'll stop recording here and we will meet on Tuesday.
थैंक यू।
Thank you.